So we had derived the Dirac equation, and I was making the point that once you apply electric fields, you could create barriers, and just like for real Dirac electrons, there can be a phenomenon where electrons penetrate the barrier without any reflection. So what is shown here holds for any energy at which we are working. Doesn't matter which energy, we always have perfect transmission at normal incidence. But I now want to focus on a particular situation. And I won't even consider a barrier which would consist of an upward potential step and a further downward potential step. I only want to focus on one step, one potential step where the potential jumps. Now, the situation could be arranged such that to the left of the potential step, the Fermi energy, or the energy we are considering for our scattering problem, lies above the Dirac point, and to the right of this potential step, it lies below the Dirac point. And we will even consider the most interesting situation where this is symmetric, where the amount of energy by which I exceed the Dirac point here is equal and opposite to the amount of energy by which I lie below the Dirac point on the right of the potential step. So now let's again consider the scattering problem and just ask, given this particular energy, what are the allowed wave vectors? So to the left of the barrier, in particular, I will have an incoming wave, and let's suppose it has this particular wave number, wave vector in the space qx, qy. I've also marked the circle of all possible wave numbers of this particular energy. Now, to the right, I also want to draw the circle of constant energy in Q space. And we already know that if we really want to treat the full scattering problem for a barrier, we usually have two waves in each region which we have to consider. So which are these waves? Well, they have to have the same energy, which means that the tip of the arrow must lie on the circle. At the same time, they have to have the same y component if I assume that's parallel to the barrier where momentum is conserved, just as before. Okay, so I get these two solutions. And usually would think, aha, I come in with this wave vector and I will proceed with that wave vector. But that's actually not true here. So let's have a closer look at what these wave vectors mean in terms of the velocity. So if we were to construct a wave packet by taking components, by taking wave vector components only around a certain given wave vector, then we would find that the speed of this wave packet, that the velocity would always be given by the derivative of the energy with respect to the wave vector. That's a general result for the group velocity of wave packets given any dispersion relation of any kind of wave. Yeah? So if I apply this here to the left of the barrier where I'm sitting in the upper Dirac cone, the velocity is just parallel to the incoming wave vector. If I apply the same reasoning and I calculate the velocity to the right of my potential step, where I'm actually sitting on the lower Dirac cone, I find that the velocity is opposite to the wave vector. So this is simple calculation. Now, so far, this is not too surprising. The same happens in any semiconductor material. If I have a conduction band and a valence band, and one of them is of a different curvature, of a different sign of curvature than the other, and something like this will happen. Okay. But now, imagine what happens if I really send a wave packet onto this potential step. It will come from the left, will proceed with this velocity, and then it certainly will not pick this solution because that would be the solution that is directly reflected. So the only admissible solution is really the one where the velocity points downward. So I've plotted that here. This is the potential step. I come in from the left, going upwards, and the wave packet must pick this particular direction corresponding to this solution. So that's a proper solution. I can match the wave functions. Energy is conserved. Everything is all right. And the velocity has changed. Now, of course, we know that if you have, say, a beam of light and it hits the surface of glass, it will change its direction. But usually, the change would be much less dramatic. Usually, it just bends a little bit. So it comes in like here, and then it will bend a little bit and proceed like that. And that's Snell's law of refraction, for example. But it will never make such an angle such as to even invert the component of the velocity it had with respect to parallel to the step. Yeah? So this is a very counterintuitive situation. And actually, it was first proposed for optical materials with a negative index of refraction, which at the time was completely hypothetical. And nowadays, people are trying in the optical and in the microwave domain to construct materials by hand, so-called metamaterials, that would have these properties and would then bend a light beam like this. Here we are not talking about light beams. Here we are talking about electron waves, but still it's quite counterintuitive. Now, not only do I have this strong deflection of the beam, but I can also look at what happens if I have other incident directions. For example, if I construct a situation like shown here, where I have a source of electrons all emanating in different directions, radially outward, and then what happens to them once they hit the interface? Well, if you look at this drawing, you will realize that I just flip the y component of the wave number, or the y component of the velocity, and what this means is that all these trajectories will refocus again in one spot. So again, this doesn't happen for usual refraction at the interface. There you would just have lines that still go out like that. So you can have focusing effects. And this is the idea behind what is called the Veselago lens. That was the a Russian physicist who first pointed out that things like this could happen, for example, in optics, if you had a material with a negative index of refraction. So now that has really been studied, proposed and studied. Again, here's the interface. Here's a source of electrons. Here are all these trajectories. Think of wave packets traveling along these trajectories. They are deflected like that, and they reconverge on some focus. So for example, what is plotted here is if you were to inject electrical current at this spot and to draw current at that spot, that you would actually be able to observe this focusing effect. Instead of just looking at the electrical current, you can also study what is called the local density of states, which is more or less a direct image of the wave function as a function of position. And again, you see these focusing effects that are predicted for situations like this. Now, this is all for what I call the symmetric situation, which is, as I said in the beginning, when the energy you're above the Dirac point equals the energy you are below the Dirac point on the other side of the structure. But of course, you could move up or down the potential value so as to spoil this perfect symmetry, so that the fixed energy level here, for example, is further removed from the Dirac point on the right. And if that happens, you can also do the calculation, and you find that the perfect focus is no longer there, and you get this kind of caustic behavior. Okay, so this is the work where this was proposed, and what you see here is actually a situation where you have this region of different potential where you get this focus. Then you get out of this region again if this is just an intermediary region, and you will find that there will be a second focus out there. And you can play games by making this region not rectangular shaped, but for example by shaping it in the form of a prism. And then you would find that if you have one source, there will be one focus inside, but you can have two focal points outside, for example. And since you have only one source and two outgoing drains, you would, so to speak, have a beam splitter if you think in terms of waves. So the incoming wave would be split into going upwards or downwards. So these are the kinds of tricks that you can play. And I mention them because these show you part of the interest in dealing with electron waves in this strange material. Now, we have been talking about these barriers admitting perfect transmission. This is nice. But on the other hand, it also seems to be bad because for a lot of applications, I really want to confine electrons to a small space in order to operate on them. And so you wonder, how is it possible to confine electrons if we have this behavior? And the answer is it's not that difficult in the end. One of the easiest options would be to say, well, at normal incidence, I have perfect transmission. So normal incidence is obviously bad. But no one tells me to use a normal incidence. And I can take a clue from optics. In optics, usually, if I have an interface between glass and air and have normal incidence, I just transmit and maybe have a small part reflected. If I have a larger angle, I can also have a refracted wave that goes into the material, and I will have a reflected wave that is reflected from the material. But in particular, I can also have a very grazing angle of incidence, and if I arrange it correctly, then I can have what is called total internal reflection. So if I'm inside the region of enhanced potential, then I can have a situation such that I'm perfectly reflected. And then, of course, I can imagine that I can exploit this to capture my electrons. So at least I could have a strip like this, or I could have a round shape like that, and by total internal reflection, I have enclosed my wave. And the same can be seen in optics. For example, if I have a ball of glass, then I can have a light ray bouncing with a very tiny angle of incidence around the circumference of the glass. And if I consider that in terms of a wave picture, I would call those modes that result whispering gallery modes. Okay? So this is one possibility to engineer your potential in the right way. There's another much more brutal possibility, which is just to cut away the graphene outside of the region where you want to have the electrons. And this is really also done by people. So they cut out or scratch or etch away the graphene outside the region where you want to have the electrons. And then you can arrange situations like this, like the one schematically displayed here, where here there would be a large region of graphene where you inject current. Then there will be a constriction. And so it will be hard for electrons to pass through this constriction. There will be a second constriction here. So you pinch off essentially a central region, which you then can call a quantum dot, where one or a few electrons can be stored. And that has been realized in experiments. So this is an experimental picture where all the bright gray would be graphene. This is the quantum dot in the middle. That would be a source contact where you can inject electrons. That would be a drain contact where you can remove electrons. So current can flow through the structure. And then you can test how large is the current depending on the potentials you apply. In particular, you can apply extra potentials by these electrodes or gates So for example, if you apply an extra potential to this particular gate, it will mostly affect the quantum dot. And if there are any discrete levels inside the quantum dots, you can shift them up and down by application of a voltage. Or also, if you apply a voltage to these gates, then you can, for example, repel electrons from this narrow constriction and make it even harder for them to get through the constriction. So these are the typical tricks that people play when they experiment on quantum dots. In this particular case, they have even gone a step further. They have implemented another narrow constriction down here. Again, current can be driven from the left to the right. But if an electron or an extra electron is present in the quantum dot, it will, of course, interact repulsively with any electron attempting to go through this lower narrow constriction. So if the constriction has already been pretty tight, then this extra electron in the upper quantum dot may considerably reduce the current going through this, what is called a quantum point contact. And that is by measuring the current down here, you learn whether there's an electron up there or not. So then people can really use this for charge measurement on the level of single electrons. Are there 1 or 2 or 3 or 4 extra electrons in the quantum dot up there? Okay. Now, this concludes what I wanted to say about potentials, but it also brings us to something else that may be important, because in the structures I just showed you, as I said, they cut out the graphene. So there's an edge to the graphene. There's a boundary where the graphene stops. And the question is, what do the electron waves do at the boundary? Okay. It turns out that this depends very much on the orientation of the bonds at the boundary. And I show here one possible configuration, which is called the zigzag for obvious reasons. Now, I claim that there will be special states that are attached to these edges that don't propagate into the interior like the plane waves that we have constructed so far, but that really are confined to the boundaries. And it's relatively easy to construct them if we just think back to our little trick of destructive interference by 3 neighboring sites. And we just have to modify that a little bit. So let's start by a situation like this. Let's claim that on these outer tips of the hexagons, I do have finite amplitude, a finite wave function. And then if the angle between these faces were 120 degrees, then I would have to pick also something around here that is 120 degrees removed, and I would have the standard destructive interference that I talked about in the beginning. But I don't know whether it's easy to see. I chose to tilt these faces a little bit with respect to the perfect 120 degrees. As a result, if I add up these 2 vectors, as it were, to get the complex number in the complex plane, the result will be a little bit smaller in magnitude. So in order to compensate it here, I need a complex number of lesser magnitude, of smaller magnitude. Yeah? So these 2 plus that one will again be 0, I claim. Okay? Now, I can extend the construction, and since the second row already has a smaller amplitude, the third row can have an even smaller amplitude, again by the same reasoning, and so on, and I can get an exponential decay when going towards the interior. And so this is an edge state. Yeah? It's localized at the edge. And it's not very different in construction than the bulk states. And so, of course, you can try to calculate this. You would make an ansatz where you say, along the edge, I have translational invariance, so I want to have something like e to the I times k, some wave number, times the lattice constant a, times m, which is the discrete index up here. But if I go towards the interior, I want to capture the exponential decay and maybe some additional phases, so my ansatz would be z, some complex number of magnitude less than 1, times to the exponent to the power of n. And so this gives me the exponential decay. This ansatz works, gives you 0 energy, and it gives wave functions whose magnitude really decays exponentially as I go towards the interior. Now, the interesting question you can ask is, how does this scale of decay depend on parameters? So, in particular, how does lambda, the decay length, depend on the k that I prescribe? Yeah? K is the wave number along the boundary. And so it turns out that you find these edge states only for k in a certain interval. And as you approach the boundaries of this interval, the decay length diverges logarithmically. Oh, like 1 over the logarithm of something that goes to 0. Sorry, like 1 over the logarithm of something that goes to 1. And so that diverges. And it turns out that these boundaries of the interval where this exists precisely correspond to the k and k prime point if you were to translate it to the band spectrum. So these are edge states in graphene. And if you like, of course, starting from the tight binding model, you can always do numerics in order to check or in order to introduce more complicated geometries that you can't solve analytically. And that has been done here. So first, let's look at the lower row where we indeed have these zigzag edges, and then what would be called a graphene nano ribbon that is a small strip of graphene between these edges. So in the y direction, it's infinitely extended. There's translational invariance in the y direction, so the momentum in the y direction, k, is still a good quantum number, and therefore what people do is simply they make an ansatz where in the y direction I have e to the I k times am, and in the x direction you just have to diagonalize a matrix on the computer. And then you plot the corresponding energies for each possible value of k, which you have picked. And so what you see here is energy versus this longitudinal momentum. You can recognize the shape, so to speak, of the Dirac cones, because if you were to make the ribbon larger and larger, what you should recover is, of course, the bulk picture, but plotted in such a way that you only plot along one of the k directions, and you don't care about the other directions. You just plot all the energies that happen to occur when you vary the other component of k, and then you would recover the Dirac cones. But what is more important is if we zoom in, that indeed there is this 0 energy level extending over a whole interval of momenta, and these are the edge states that we have just discussed on the previous slide. So they are there even in numerics. And they would be important. For example, transport could occur along the edges of the sample by electrons traveling along these edge states in principle. Now, there's another shape of the boundary, which is called armchair, also maybe for obvious reasons. And it turns out that if the edges are of this type, there are no edge states. Yeah. So edge states are restricted to the zigzag configuration. And of course, now you could start thinking about more complicated geometries, yeah, where the boundary is more complicated, and then you alternate maybe between zigzag and armchair, and if the zigzag edge state regions are close enough together, you might have quantum tunneling between one zigzag edge state and the next adjacent zigzag edge state, because maybe the intervening region of armchair is short enough. Okay? So these are edge states in graphene. Now, all of what I've said up to now is really directly from the tight binding description.
Can I just frame this? Keep talking.
Okay. discussed came by expression of trying the Dirac equation, but input, because the Dirac equation, of course, doesn't know whether you have an armature edge or a zigzag edge. So you have to put that by hand. And so you have to figure out, starting from the tight binding model, what would be the correct boundary conditions if you had, say, a zigzag edge. Now, in principle, we know that just starting from the picture of the wave function, if I assume that the atoms at the tips of the hexagons are my A lattice atoms, then what I learned from this picture is that I can arrange the edge states such that the amplitudes on all the B lattice points are simply 0 because of destructive interference again. So in the Dirac equation, I should prescribe that. I should just demand that the amplitude on the B lattice should be 0 at the boundary. So both at the K point and at the K prime point, the B component is just prescribed to be 0, and apart from that, I need no other boundary condition. And then from the Dirac equation, I will also find the edge states. Of course, what I find in the Dirac equation will only be valid just near the K or near the K prime point. Everything in between, of course, is outside the range of validity of the Dirac equation. Okay. Any questions so far about the edge states? Okay. Let me then start the discussion of the last bigger topic that I want to touch. And that is what happens if we place these electrons in a magnetic field. And we will see that it differs from the standard behavior of electrons in a magnetic field. But first, let me remind you of what would be the standard behavior of electrons in a magnetic field. And so the simplest thing you know is that electrons are charged particles. In a magnetic field, they will feel a Lorentz force. The Lorentz force is perpendicular both to the velocity and to the applied magnetic field. And so if my motion is inside a plane and the magnetic field is perpendicular to this plane, the Lorentz force will always be perpendicular to the motion, and it will force my charged particles on a circle. So I get the circular motion, which is also sometimes called cyclotron motion. One of the more interesting facts about this is the following. The radius of the circle does depend on the velocity. If I shoot in a particle with very high velocity, the radius will become quite large. But the frequency of motion is always the same, irrespective of radius or velocity. The frequency is always the same. It's called the cyclotron frequency. It's linear in the size of the applied magnetic field. Okay. So now I have a classical problem of motion where the frequency is independent of amplitude. I know of one other classical problem where this is the case. That is the harmonic oscillator. Yeah? In the harmonic oscillator, the frequency is independent of amplitude. And as a consequence, if I quantize the harmonic oscillator, all the energy levels in the quantum problem are equally spaced, and the spacing is just given by h bar omega, omega being the frequency. Now, because of that reason, since the same happens here, I have a frequency independent of amplitude, I also get equally spaced energy levels for the cyclotron motion of electrons treated quantum mechanically. And these are called the Landau levels. Now, in contrast to the harmonic oscillator, these Landau levels are highly degenerate. That, roughly speaking, corresponds to the fact that you can pick this cyclotron orbit and smear it a little bit to claim it's quantum mechanical. And you can still place it at many different points on the plane. And you just count the number of different points you can place it on the plane with an area roughly given by the size of the typical orbit. And that gives you the degeneracy of each of these Landau levels. And the higher Landau levels would just correspond to a larger radius. So the radii of this motion would be quantized. The higher Landau levels would correspond to a larger radius, roughly. Okay, so these are the Landau levels. Then if you want to treat motion or transport, electric transport, you would at first be disappointed because it seems, oh, these electrons just move around in a circle. So they are stuck. They don't transport current. But looking at it more closely, you figure out the following. Every real sample has boundaries. And at the boundaries, I don't have circular motion. Rather, I just have, say, half a circle. Then I have reflection from the boundary. And so my electron will be skipping along the boundary. Yeah? These are really called skipping orbits. And depending on the sign of the magnetic field, all trajectories, say, on this left-hand boundary will be skipping in the same direction, say, upwards, like shown here. Whereas all the orbits on the other boundary will be skipping downwards. Okay? Now, if I translate that to quantum mechanics, I arrive at edge states. Now, these are edge states of a different nature produced by the magnetic field, but still edge states. So each of these skipping orbits turn into edge states. And these edge states are important for transport. For example, if I put a few more electrons in the edge state traveling upwards, then I will get an overall current in the sample going upwards, because it's not compensated anymore by an equal but opposite current on the other side of the sample. So that is how people treat transport in the quantum Hall effect. And then they would find the following, and this will become important in a minute when we treat the same for the Dirac equation. Then they will find that if I change the Fermi level such that more and more of the Landau levels get filled, for each new filled Landau level, I will get an additional edge state occurring here, which also can transport current. And that means if I calculate the current carried overall, there will be steps. Whenever I pass a Landau level, I get a new edge state opening up, which gives me 1 unit of current. Okay. So much for the standard situation. Now let's take a graphene sheet and put it inside a magnetic field. So here's the magnetic field. Let's just assume for a moment we have a small, narrow graphene nanoribbon like shown here, because that's where people here made numerics. And what they find is the following. Again, energy versus one of the momenta. We will see in a moment that it's fair, that there's still one momentum left as a good quantum number. We still see something at zero energy. That's not too surprising. We would have expected the same for the standard edge state without magnetic field. But what we see in particular are there occur other levels, new levels that are flat in energy. So the claim then would be these are the Landau levels of graphene. Of course, one of the things you see here is they are quite obviously not equally spaced. So this will be one of the things that one has to explain if one makes a theory of the quantum Hall effect in graphene. Okay. Now then, instead of taking this tight binding approach, which was what they did for calculating these numerical energy dispersion relations, let's just pick the Dirac equation. So again, here's my infinitely extended graphene sheet, X and Y. And in order to describe a magnetic field, in my Dirac equation, I first have to understand how I couple my electrons to the electromagnetic field, but that is well known. It's the same for the Schrödinger equation and for the Dirac equation. It's known among physicists as minimal coupling. What really happens is that wherever you spot your momentum operator, minus I times gradient, you add an additional term that goes like the vector potential. So you couple to the vector potential. Now, one of the first steps whenever you face a problem such as this is to pick a vector potential whose curl will be the magnetic field that you prescribe. And there are many different possibilities. You just have to choose your gauge. But for this problem, the most convenient gauge is the Landau gauge, where you would have the vector potential only depending on one of the coordinates, let's say the y coordinate. So the x component of the vector potential is minus b times the y coordinate, and if you take the curl of this, you will find it corresponds to a magnetic field pointing out of the plane. Okay, so this is the equation we want to solve, the 2D Dirac equation with the vector potential. Since the vector potential does not depend on x, we can make this ansatz where along the x direction we still have plane waves, e to the ikx, but in the y direction we cannot tell at the moment, so it's phi of y. Now if I insert that into the Dirac equation, I arrive at the structure shown here. This at first sight may not look very familiar, but we can take a hint from the solution of the non-relativistic quantum Hall effect, where I already indicated that it's very closely related to the harmonic oscillator. Actually, if you pick a gauge like this and you write down the Schrödinger operator together with the vector potential, you will quickly find that you directly have a harmonic oscillator potential that is shifted by an amount given by k. Now here it's maybe not so obvious, but if you look more closely, you see there's always a combination of the derivative, that is the momentum, and the coordinate y. And now you remember that the standard way to solve harmonic oscillators with operators is, of course, you introduce annihilation and creation operators, and they are of the structure coordinate plus plus the momentum. Like this. Okay, so x plus IP essentially. And we spot the same structure here, the momentum and the coordinate. So that means you want to introduce this combination y. You want to introduce the combination of momentum and coordinate, but before doing so, you want to go to dimensionless coordinates in order to make everything simpler. And so it turns out that with respect to the length, there is only one combination that gives you a length here that you would call the cyclotron length, which shrinks with increasing magnetic field. That's the same you observe also for the non-relativistic problem. And there's the frequency. In our case, the cyclotron frequency cannot possibly be the same expression as for the standard non-relativistic case, because there was mass in the denominator. We don't have any mass. So it turns out that here it's the velocity in our Dirac equation divided by the one length scale we have. And that, of course, gives you a frequency. Okay. So now I can introduce a coordinate properly made dimensionless by dividing by LB, and also shifted by k, because the structure here is always that there's this combination between y and k. So along the x direction you have plane waves, but along the y direction the claim is that in the end we will get wave functions that are tightly localized in the y direction and only infinitely extended in the x direction. This is the same kind of game that you also see happens in the non-relativistic case. Okay, and now you can introduce your operators, which are of the form coordinate plus I times momentum and the corresponding adjoint operator. And if you re-express the Hamiltonian in these operators, it will be of this form. And let me spend a little bit on this form. So this combination obviously appears in the off-diagonal elements of this matrix. The matrix is the one which corresponds to the A and B sublattices. And if I have something appearing in the off-diagonal element, it just means that it picks an amplitude for the B sublattice and turns it into an amplitude for the A sublattice. So in order to denote that, I say, oh, sigma plus is supposed to be the operator that goes from B to A. Sigma minus will go the other way from A to B. And then I have to multiply these operators, A or A dagger, with the corresponding operators that switch from A to B. Yeah? So I have this two-dimensional subspace that corresponds to A and B sublattices, and I have my harmonic oscillator operators. And now that is a funny Hamiltonian because it occurs in a completely different setting in physics. If you were to think of an atom and approximate it by just two levels, ground state and first excited state, and then you couple it to the electromagnetic field inside an optical cavity, you would describe that field in the simplest version by one mode of the field, that is one harmonic oscillator. Then the simplest thing that can happen is that, say, your atom is excited and it decays to the ground state and at the same time puts a photon into your optical cavity. And that would be described exactly by a process like this. So what did I say? So the atom is de-excited, sigma minus, but a photon is created, A dagger. And of course, there's the other process where the photon is absorbed and the atom is excited. So actually, we know how to solve this Hamiltonian. The only difference with respect to the story with the atom and the cavity is that an excited atom has a larger energy. And also, if you put a few more photons into the electromagnetic field, you increase the energy. These terms are absent here, so it's even simpler here. But apart from that, it's the same structure. And for the case of an atom coupled to a mode of the electromagnetic field, this is known as the Jaynes-Cummings model. Okay. Okay, so now we want to solve this. It's easy enough because if you think about it, if I have n excitations in my harmonic oscillator and then I apply, say, this first term, then I will destroy one of the excitations and I will go from, say, B to the A sublattice. And the only other thing that is possible afterwards is to reverse the process. So this, even though it has an infinite dimensional Hilbert space, it decomposes into many two-dimensional Hilbert spaces. So again, here's the Hamiltonian. These are the two-dimensional Hilbert spaces. I can either have the nth excited state of my harmonic oscillator in the upper component, or I can go towards the lower component and at the same time lower the excitation number of my harmonic oscillator. And then if I apply the other part of the Hamiltonian, I just go back. And the amplitude for this process to happen, that is the amplitude for this operator to connect this to that state, is just square root of n. That is because of the matrix elements of the harmonic oscillator operators. Yeah? So if I have a harmonic oscillator in level n and apply the annihilation operator, I will get square root of n times n minus 1. Okay. So then certainly you can diagonalize a Hamiltonian that only has two off-diagonal components that look like square root of n, like this. And the energies will just then be plus or minus square root of n times the cyclotron frequency. So this is the energy spectrum of the 2D Dirac equation in a magnetic field. Has a level at 0 energy and levels at not equally spaced energy levels at square root of n. And again, this was found a long time ago at a time when there was no means of really realizing this in the laboratory. And you would find the same spectrum at K prime, by the way. So now, if people want to study this in the laboratory, what do? They do electrical transport measurements, like in the standard quantum Hall effect. And what do you expect? Well, the story is very similar to the standard quantum Hall effect. Whenever the Fermi energy lies between Landau levels, you find that electric current is transported along the edge channels at the boundaries of the sample that correspond to those skipping orbits. So let me go back to this picture here. You would draw a diagram like this. You would find in the bulk of the sample, the energies of the Landau levels are below the Fermi energy, or here it's denoted as chemical potential mu. It's the same thing for us. But at the edges of the sample, the Landau levels would bend upward and really cross the Fermi energy. And that's where they are important for transport. Yeah? And then you would count, you would say, aha, here in this case, I don't know, 2 or 3 if we count that one, edge channels contribute to my current. And whenever my Fermi energy is raised even below yet another Landau level, another edge state will kick in. And so that means if you plot the current versus the Fermi energy, you expect it to be constant for a while and then jump to another level. And these are the famous quantum Hall effect plateaus of the conductance. So let me show them to you. So here, just focus on the red curve. This is experimental data. This was one of the first experiments done in 2005 to prove that they did have obtained single-layer graphene, and it did show these properties predicted by the 2D Dirac equation. And so the red curve is really the Hall conductance, that is current divided by, essentially current divided by voltage. It has the stepwise behavior. And the current, by the way, is transported without dissipation. Yeah? There is no scattering really going on at the edges of the sample. Again, this is a feature shared with the standard quantum Hall effect. And again, it can be quite easily understood even in a classical picture, because if you have these skipping orbits, and now you perturb the sample somewhere by having some disorder, then the skipping orbits can just skip around this point. And the other orbit that goes downwards is very far removed at the other edge of the sample. So there's really no possibility for these electrons to be scattered by some impurity to the other side of the sample, which they would have to do in order to travel in the opposite direction. Yeah? So this is what makes transport dissipation less. And that is shown if you plot the resistance, the longitudinal resistance is exactly 0. So that's the purple curve, is exactly 0 when we have these plateaus. But whenever you have the transition between the plateaus, it rises. Okay. And what you can see, in particular from this curve, is that at 0 Fermi energy, you get a transition between different plateaus. But the transition between different plateaus happens whenever you cross a Landau level. So that tells you, yes, there is a Landau level exactly at 0 energy. And that's a specialty of graphene. And this is one which we got out of this calculation, but it actually can be traced back to the fact that the electrons turning around their circles in a magnetic field pick up this extra phase of pi, this extra Berry phase of pi. That can be connected to this peculiar arrangement of the energy levels. Okay, so this was one of the very early and very important experiments. Now I'm almost finished. So these were the most important things to know about graphene. What happens with the potential, what happens at the edges, what happens in a magnetic field. And in the remaining minutes, I just want to give a brief overview of all the other fun things that there are to do once you have mastered the basics. Okay, so now nothing is perfect. So there will be disorder in any material. And a relatively natural kind of disorder to occur in graphene would be that the lattice is not really perfectly flat, but it's distorted, for example, by these ripples forming or in any other way. So the lattice is distorted. Perhaps it's lying on a substrate, and so it's forced in some non-ideal positions of the atoms. It turns out that if you insert the disorder into the tight binding Hamiltonian, it can, of course, occur in 2 different ways. First, the energies of different sites may be shifted. But also, as was remarked in the beginning, the bond lengths could be altered, and that would change the tunnel coupling. So both can happen. If the energies of the sites are shifted, you can express this in the Dirac equation simply by an extra potential. And in the simplest case, if the this order is smooth enough, then this potential would not distinguish between A and B sublattices. So it would be of the kind that we had discussed earlier when we discussed the Klein barrier, the Klein paradox. But then if you insert this order into the tunnel couplings, you find that with respect to the Dirac equation, this happens to be equivalent to an extra vector potential. Interestingly enough, at the K prime point, it's the negative of this vector potential, and it should be like that because introducing disorder by deformation does not break time reversal invariance. So it's not like a real magnetic field. So there should be a difference between a real magnetic field and this kind of fictitious magnetic field, and the difference is shown here that there's a different sign at the other K point. Okay, so this is already interesting. Then you can ask, well, what happens about point defects? And it seems that if you then solve the Dirac equation, you can get wave functions that look like this, like 1 over r. It looks a little bit localized, but if you square it, 1 over r squared, and then you try to integrate it in 2 dimensions, of course, you get a logarithmically divergent integral. So these are called semi-localized states. Yeah? But of course, for finite samples, they can still play the role of localized states. This is just point defects. What about more long-range potentials? For example, if I really have a charge defect, or just a point charge nearby the graphene lattice, it will create a Coulomb potential. So first of all, you have to ask yourself, what is the Coulomb potential in graphene? And then you shouldn't make the mistake to say, it's 2 dimensions, so I should solve electromagnetism in 2 dimensions. You don't, because the graphene sheet is just embedded in real 3-dimensional space. So the Coulomb potential between 2 charges is still 1 over r, the standard 1 over r. Okay, so you start with 1 over r. Then you solve the 2D Dirac equation. You find many things that are similar to the 3D massive Dirac equation. In particular, you find that if the central charge is too large, something drastic happens, similar to the standard Dirac equation. Namely, the theory would tell you that if the central charge is too large, that is, this coupling constant is too large, then the electron falls into the center. Now, fortunately, for graphene, we don't have to stop at this point. We know exactly that we can always have recourse to the tight binding description. So then you would go back to the tight binding model. It would tell you that a new localized state develops at the center, which is split off from the original band, and that, of course, can't be described by the Dirac equation because it would contain very high wave numbers. Okay, so this is what happens here. Oh, another very nice topic. Here, this is, so to speak, my favorite effect. Suppose that someone has decided to eliminate one of the hexagons and replace it by a pentagon. This actually happens, for example, in other, so to speak, graphene-based materials. If you think of, there are these buckyball molecules made of carbon atoms. They look like a soccer ball, exactly like the old soccer balls. And they consist of pentagons and hexagons. And so you can just imagine a graphene sheet that is, so to speak, rolled up in a kind of cone, and at the tip of the cone you have a pentagon. Now, in order to make this happen, and in order not to spoil the hexagons everywhere else, you could take a 60-degree wedge out of the original graphene sheet and then glue together these edges, like shown here. This recovers the perfect hexagonal structure everywhere except for in the center. But the funny thing is that now you identified the A and B sublattice points at this edge. So red has to be identified with green, green has to be identified with red. So the situation is somehow strange because locally everything looks all right far away from the center. However, if you traverse once around the center and you started off in A, you will end up in B. So in order to, and you don't know where exactly this happens. Yeah, it's not that this line is in any way special. It somehow just happens while you traverse around. And we have similar situations whenever we have a vector potential. So in total, the particle adds up a phase from the vector potential, but you don't say at which point this happened, because there's gauge invariance. You can pick a different gauge, then it will pick up more phase at this part of the trajectory than at the other part. And it turns out that in order to describe the situation here, you also have to introduce a vector potential like that, but slightly more complicated, because now it can also mix k and k prime. How do we see that you can mix k and k prime? Well, for me, the easiest way to realize that this is true is, look, here I have a wave function propagating like this 60 degrees in the upward direction. Here I have a wave function propagating in the horizontal direction, and they should somehow be identified, yeah? But if I rotate by 60 degrees my wave functions in real space, I also have to rotate by 60 degrees in k space, and a rotation by 60 degrees in k space just takes me from the k to the k prime point. So that's why the Hamiltonian written down here is then of a structure unlike any what we have discussed before, namely it mixes k and k prime. And so people say that this is a non-abelian gauge potential in contrast to what you introduce here. Okay, a few final things. I already remarked that electrons in graphene are pretty insensitive to disorder. That is because if you try to backscatter them directly, it's no good. The matrix element vanishes. Yeah. So what really happens is they just slowly change the direction of travel as they feel the forces from the potential. Okay, so be that as it may, whenever you have electron waves traveling in a disordered potential, there's a very generic phenomenon, and that is that you have backscattered waves that interfere constructively. So in a path integral language, people tend to say that if I start from this point, I want to return to the same point by a closed trajectory, I can traverse this closed trajectory in one manner or in the other manner. And since it's quantum mechanics and it's coherent, I have to add the amplitudes, not add the probabilities, and then only square to get the probability to return to the same point. And I will have constructive interference, and this will enhance the probability to return to the same point, and this will enhance the electrical resistance. And this is an effect which will get destroyed at higher temperatures, because then interactions among the electrons will tend to destroy the phase coherence. Okay? So this is called weak localization usually. But for graphene, it turns out that if you go around these trajectories, then of course, because the helicity is conserved, also the spin has to go around. So you start with a spin pointing forward, you go back to a spin pointing in the backward direction. This doesn't give you a phase of pi, like here, which needed a full 360-degree turn. It just gives you pi half. But on the other trajectory, you will get, so to speak, minus pi half, and then there will still be a phase difference between the two of pi. And so instead of constructive interference, you get destructive interference. And if there's destructive interference, they are less likely to come back to the same point, and so electrical resistance is actually lowered. So this is then just the opposite, and is called weak anti-localization. Okay. Then if you just ask about the conductivity without disorder, like of a strip of graphene, like shown here, you apply a voltage, measure the current, and do that as a function of Fermi energy, you find, first of all, what is not surprising, if you have a large Fermi energy, you are already deep up into one of the Dirac cones, and then many electron states will contribute, because the circumference of the circle of constant energy gives you, so to speak, the density of states, the states contributing to transport. So it's no wonder that as you raise the Fermi energy, more and more electrons contribute, current gets conducted better and better. It's just the density of effective charge carriers increases. But even right at the Dirac point, where nominally the density of states is 0, you always get a sort of minimum conductance, and it is very fundamental in the sense that it's only connected to the elementary charge and to Planck's constant. So for example, the velocity does not enter here. It's E squared, so the current divided by voltage would go like E squared over H That's the fundamental prefactor. And then, of course, the geometry, that is the width of the sample divided by the length, would enter. And this behavior is not surprising in principle. This behavior would be the behavior you expect for a disordered metal that really has resistance, that has a finite resistivity. If you make it longer, the resistance just goes up, or the conductance shown here goes down. That's not surprising. The surprising thing is that if you take ballistic graphene, like here, without disorder, it still shows this resistance, and it's fundamental. Yeah. Okay, and finally, a fun fact of graphene. We have always talked only about the properties of electrons, but you can also ask, say, what about optical properties? And the simplest thing you can do is take a sheet of graphene and shine light through it. And the fact is it's fairly transparent, but about 3%, I guess, about 3% of the light will be absorbed. And if you analyze that more closely, how strong should be the absorption, it turns out that this absorption also becomes universal. It does not depend, for example, on the Fermi velocity or on the tunnel coupling or on the lattice spacing or any such material details, but it's rather given, the absorption is given by pi times the fine structure constant. And this is the real fine structure constant of real electrons in vacuum. Now, this is funny, I think. They don't still sell it as a way of precision measurement of the fine structure constant. And the reason is that if you really take optical photons, then the electrons get excited by fairly large energies on the electron volt range. And these are energies where you see first deviations from the simple Dirac cones. Because as you go away from the Dirac points, of course, finally you should see the full band structure that we showed in the beginning, which doesn't look like Dirac cones. And then this fundamental universal behavior breaks down. So it's only approximate, but I still found it quite interesting when I first read about it. Okay, thank you very much.
Thank you very much for your nice introduction into this topic. Are there questions?
Yes, I've got a question on these defects that you like so much. There was quite a lot of work in three-dimensional gravity. Jacques and Prof studied these. Is that the same mathematics?
Oh, yes. So actually people studying this make a connection to the Dirac equation on curved spaces. Right. And I'm not an expert in this, but it's really apparently mathematics that's right. Closely related to what people also do in cosmology.
Okay, then the second question is, can you get two defects to interact? Is that possible, or are they always locked in the lattice? And
these defects should be thought of as frozen by when the material was formed or when it was put on a substrate. But you can at least consider situations where you have two defects, like for example, pentagon and heptagon will cancel each other, so to speak. Mm-hmm. Pentagon is like vortex, yes. Heptagon is like anti-vortex. Yeah.
So that can be done, and then
that can be studied at least, and that I don't know whether there are experiments that already study that in detail. Yeah, but this seems to occur fairly relatively naturally. These are graphene sheets that are no longer flat, but somehow bent into cone-like structures. Mm-hmm.
So, if you want to consider electron-electron interactions,
mm-hmm.
do you do it via a many-body Dirac equation or rather via a Hubbard model?
Well, of course, you could always start from the tight binding model and then it would be a Hubbard model. What people try to do is, of course, start from the Dirac equation and then exploit the particularly simple form of the band structure with the Dirac cones. Yeah. And so one of the things to notice here is that since the density of states vanishes near the tip of the Dirac cones, also the tendency to screen electric fields is very low because there's a zero density of states right in the Fermi energy when we are neutral.
Maybe I can ask a question concerning this. You didn't talk about any physical effects in the many particle case. Are there also funny effects that occur for more than one particle?
Well, probably there are, but the situation there is far, far less resolved than for these, and I'm really not an expert in those.
Yes.
One sort of general invitation. I mean, you describe these simple models like this Hall effect, which are exactly soluble, or you talked about some numerical work, and it all seems to fit with the experiment. So it's kind of, you make it sound like a closed subject. But if you were to sort of set homework to mathematical physicists coming from this subject, where are the kind of big questions that seem a real mystery or surprise that are not understood from your point of view?
Well, okay, so I would not maybe start with the interaction effects, because they're, even to the physicists, it's quite open. Now, for example, if you go for mathematical rigor, then even the fact, or even the question, when do you get these Dirac cones, when do the bands touch, under which circumstances, that seems to be relatively difficult. There seems to be a recent paper by Pfeffermann et al. Who have proven that if you don't start from the tight binding model, but really take a smooth landscape for potential, but with the same symmetries, that then under certain conditions you can prove that you get these Dirac cone structure, yeah, which is not so easy apparently. And then if you were to add interactions to that, it could become very difficult, I guess. Also, all these, this defect physics, I think, is a very nice playground. Yeah, I'm sorry for giving this impression. I just took the elementary stuff, and then maybe you feel inspired to attack the more difficult stuff.
Well, last chance. No, the party is waiting, but thanks a lot.